Hello everyone, welcome to problem 2.9 of David Griffiths Electrodynamics. Let's jump right in. So this problem states that we have to, suppose we have an electric field given to us here of k times r cubed in the r hat direction, and this is in spherical coordinates where k is just some constant. It wants us to first find the charge density rho. That's the charge density creating this electric field. And then B, find the total charge contained in a sphere of radius r centered at the origin, surrounding this charge density. All right, so part A is to find the charge density rho. And this can be done pretty easily. So in this section, we learned about Gauss's law and integral form and differential form. And this is where the differential form of Gauss's law comes into play. So we know that the differential form of Gauss's law states that the divergence of the electric field is equal to the charge density divided by epsilon naught. So we have the electric field, so let's try to calculate the divergence of this electric field. And our electric field is in spherical coordinates, and it only has a r hat component. We don't have a phi or a theta component. If you look in the, the cover of Griffiths' book, you'll find equations for how to calculate the divergence in various coordinate systems. And so I'm just going to write that out here. So the divergence in spherical coordinates for, where we only have the r component is given by 1 over r squared, the derivative with respect to r of r squared times the r component of our electric field, so which is just kr cubed, so k times r cubed, and that's it. So just simplifying this a little bit more, we have 1 over r squared, the partial derivative with respect to r of k times r to the 5th. All right, so this is just going to be, let's calculate the derivative. So that's going to be 1 over r squared times k times 5 r to the 4th power. And then canceling out our r squared term on the bottom. So we have that the divergence of our electric field is equal to 5k r to the r squared power. And this is equal to the charge density rho divided by epsilon naught. And therefore, the charge density rho is then equal to, just multiplying on both sides, we have 5k epsilon naught r squared. And this is our charge density. All right, so part B says to find the total charge contained in a sphere of radius r, big R, centered at the origin. And it says do it 2 different ways. So we're going to do it by first direct integration, by just brute forcing the integral. And then we're going to use Gauss's law in integral form to show that it's a little bit easier to do it that way. So part B, let's do by direct integration. So given that we have our charge density rho here, then the total charge Q is just the charge density rho times the total volume. Or really, you can write this as rho times the integral of dv, where I should really put rho inside the integral because our rho is not a constant with respect to this integral. Our charge density is a function of the radius. So really, I should write this as the integral of rho dv. So essentially, we're just going to integrate our charge density over the entire volume of the sphere of radius r, and that should give us the total charge contained. All right, so let's go ahead and do that. So this is going to be a triple integral and spherical coordinates. So we have our total charge Q is equal to, so dV is a differential volume in spherical coordinates, and that's going to be given by, I believe it's, let me just take a look here. So r squared sine of theta dr d theta d phi. So let's go ahead and write out the phi integral. So we have integral from phi running to 0 to 2 pi. And I can bring out actually the 5k epsilon naught out to the front. So 5k epsilon naught. Those are just constants. And then we have d phi. Nothing in our integral depends on phi. Then we have our theta integral, 0 to pi. And the only thing we're integrating here is sine of theta, d theta. And then our r integral runs from 0 to capital R. And that's going to be r squared. That comes from the differential volume element. But then we also have an r squared coming from our charge density. So it's actually going to be r squared times r squared. I'll just write that out. And then dr here. And so this integral, the phi integral, just becomes 2 pi. And the integral of sine of theta d theta from 0 to pi is a pretty simple integral. That's just 2. So we have 10, actually 20, because I have 2 pi times 2 times 5. So that's 2 pi times 2 is 4 pi times 5 is 20 pi. So we have Q is equal to 20 pi k times epsilon naught. So that's just taking these integrals and evaluating them. And then we still have this r integral from 0, r equals to 0 to big R of r to the 4th dr, which is very simple. So this just becomes, this is going to be r to the 5th over 5. So we have 20 pi k epsilon naught r to the 5th divided by 5. So 20 divided by 5 is 4. So this is just equal to 4 pi epsilon naught k r to the 5th. And this is the total charge contained in some radius, in some sphere of radius r surrounding our charge density. Oops, there you go. All right, so that's the method of direct integration. We didn't use Gauss's law, we just integrated the charge density over the entire volume. So now let's go ahead and use Gauss's law and see if we can get the same answer. So by Gauss's law, we know that the flux of the electric field, so that's the integral of E dot dA through our Gaussian surface. So our Gaussian surface is just going to be a sphere of radius r, little r we'll say, surrounding our charge density, whatever distribution that is. And that's going to be equal to the total charge enclosed in our Gaussian surface divided by epsilon naught. Right? So at our Gaussian surface of radius r, the electric field is going to be a constant. And we can just pull that out of the integral and say that this is the integral over the surface area of our Gaussian surface, essentially. So that's just going to be E times 4 pi r squared. And then on the other side, we have Q enclosed over epsilon naught. So what is Q enclosed? That's what we're trying to find, right? This is the total charge enclosed in our Gaussian surface. So our Q enclosed is just equal to this. We just multiply by epsilon naught. So we have epsilon naught E 4 pi r squared. And you can make this capital R, big R, whatever you want to make it. I just made it little r. And so the electric field then is just given by, we already know the electric field. It's given to us in the problem. So it's going to be K times K times R cubed. So our Q enclosed, the total charge enclosed in our Gaussian surface then, is equal to, we have 4 pi epsilon naught, then E is going to give us K times R cubed times R squared, that's R to the 5th. And if you look back at what we had over here, by direct integration, we have 4 pi epsilon naught K R to the 5th. So our answers do match. Gauss's law does give us the same thing, and we don't have to do the triple integral, which just makes life a little bit easier. So it was just kind of show you how Gauss's law can simplify some problems given certain symmetries. And that's pretty much it for problem 2.9. It's a very short and sweet problem. So if you guys enjoyed this video, please be sure to drop me a like and subscribe if you haven't already. Please give me feedback and comments down below. If you find something I did wrong, if you find errors in my videos, let me know. Or just have suggestions for future problems you want me to solve. Feel free to tell me in the comments below. And as always, have a good day, and I'll see you guys later.